Hi everyone. Apologies for being late. John, Grace, how are you?
Hello, sir.
Yeah, sorry for being. I was on multiple meetings. Hi Grace, how are you? Are you on work today, Grace? I see, I see. So, yep. Um, yeah. Hope. Well, tomorrow we'll have a hands-on with John also. But today is also a hands-on session. So it's pretty exciting because it's about visualization and we'll be using mostly Matplotlib. But I want to introduce to you Plotly. Maybe on Saturday, if we can finish all of the coverage for this meeting, we can discuss Plotly, which is like an interactive, like Power BI, an interactive charting library in Python. So let's wait for a minute and then we should start. John, were you able to finish the discussion of the test yesterday? That discussion would really help them by the concept for going through
We only
those.
finished the t-tests independent and dependent, but it covers the assumptions as well as
Mm.
the non-parametric counterparts
Parametric
whenever
control.
the yes.
Did you discuss Man with you?
Yes, Man Whitney
Okay,
and
Man with you.
Wilcoxon.
Wilcoxon. Okay, both. Awesome, awesome. Non-parametric tests are not common in the industry because they have voluminous data. So they take advantage of um the central limit theorem. They always invoke it. That's why you would rarely see non-parametric tests in the industry, particularly with large companies. But with experimental research, like those involving like development of new drugs, so typically it's expensive and they have a limited amount of uh, grant funding. That's why they keep the samples really low. That's funny. If you think about it, with market research, they have tons of fund, but for something that is will will ultimately help people in the future by discovering new drugs and effective treatments, they have limited funds. So there's an irony to that. Anyway, hi Hasiba, welcome to the meeting. How are you?
Hello everyone, thank you. I'm good. How about you all?
Yep. Yeah, I'm doing great. I was also late. I just joined maybe a minute earlier than you. Had to
Yeah, I just
attend
saw
some
your
other meetings.
message and I just went to feed the kids, then come back and start.
Yeah, yeah. Being a mom is difficult, right?
Oh, yeah. Yeah.
You're not only living your life, you're living um like the lives of your children. You're
Yeah, having
responsible
kids is lots
for
of
the
work.
welfare. Yeah,
Yeah.
the most difficult, but I think the most rewarding one. You cannot
Yeah,
equate that to
rewarding. Sweet
any amount.
moments. Yeah.
Yes. So yeah, let's start. So I did not prepare any PowerPoint presentation for today because I made this in a way that um, it will be hands-on. So I suggest you guys open your Colab. And John, can you share the Iris? I'll send it through Messenger. Can you share to the group this data sets? Let me see. Because it would be best if they can go through each of the visualizations today. Let me see. Hmm. Even my computer is hanging now. Where is it? Statistics. What happened? Did I just
Wait,
uh
hello there. Do you have an access to the Discord?
I don't have any access.
Oh, wait. For some reason, I can't open the Discord. So I think it's better if we will share it through their email.
Okay, okay. Or alternatively, I can just create a drive and then share the link in the chat box. I thought I got dropped. Um, my computer is acting up. Let's see. So I think this is the most efficient way to do this as compared to having it sent through email. I'll create a new folder, and then data set for lecture 4 or lecture 3 rather. Then I'll have it inside here. Hmm. Yeah. Share, copy link. Great, Nasiba, can you please try accessing this share folder? You should have access to the data set. If you can open that, um, have to change the. Yeah, please let me know if you have it. And Grace, do you have it? Yeah, your volume is quite low, Grace. Uh, uh, I sent a link in the chat box to my Google Drive, so you can just download it from there. I'll just adjust my AC for. It states request for permission has been sent. Yeah, let me see. Um, There we go. Share. Do you have it? I just I just approve your request for access. Yeah, we'll be using all of those files. So please download all of those three. So we'll be using Iris, dataset, data science, CSV, as well as the other one. So please download all of them. Okay. All good. Yes, Hasiba, I also accepted yours. Um, Maybe try refreshing it for a while, and you should be able to access it. Or maybe you're accessing it in a different email. Yeah. Originally, originally I can attach things in the chat box, but for some reason I don't see any any options now. I don't know what happened. I asked Sherry about it, but she told me that uh she did not change anything.
The same case for me, sir.
Okay, maybe it's just about maybe about the update because of the update in the teams. Hasiba, Grace, do you have the files? Okay. How about you, Grace? Do you have them? Oh, Jeff got the job. Is it the probably the analyst job that he applied for earlier? You should congratulate him. Okay, I will try. Grace says I will try to access through my work desktop, which requires sending to work email. So move on, and I'll catch up. Sure. Thank you very much, Grace. So yep, I'm sharing my screen. So basically, the focus for today's lecture will be data visualization. And data visualization is something that we already talked about during the Excel session. However, it's not sufficient that you know how to do visualizations in Excel, but it's quite easy to do that in there, right? If you can if you can create pivot tables, then it would be very easy for you to create visualizations, whether for categorical, whether for numeric data. But again, um, this is not a one size fits all thing. Every visualization has their own set of requirements. So for categorical data, basically you'll be presenting those things in terms of percentages and counts, right? And can you identify, Tasiba, different visualizations that we can use to present frequencies and percentages, or in general for categorical data? Tasiba?
Can you please repeat? I didn't hear
Yeah,
you.
sure. For example, you have a categorical data and you have the following statistics on the form of percentages and frequencies. What visualizations or charts can you create from that kind of data and statistics?
Uh,
Okay, let's make it specific. You have a variable educational attainment of 100 people, and they are distributed from no education at all, um, finished elementary school, finished secondary, college graduate, and advanced degree. How would you present that? What chart will you do from that kind of data?
uh, data frame? Or
Yep, a data frame is a structure to store our
yeah.
data set, right? It
So
is
the
like
chart may
your
be a pie plot
okay,
or
a pie plot or
matplotlib.
a pie
Yeah.
chart. Yep.
Yeah.
Um, so you can create pie charts from that kind of data if you want to present the distribution in terms of percentages, right? Proportion proportion of a certain category from the totality. And you can also create bar plots, right? Bar charts from it. It could be a horizontal or vertical bar plot. It's only a matter of preference between the two. And of course, if your data set is, say, numerical, like sales throughout the year, um, then you will not do that in bar plots, right? For the reason that you want to see trends, seasonalities, and cycles. So, in order for you to effectively visualize those things, you will use a line plot, right? And also for a numerical data, if you want to see how at least two variables interact with each other, then it's best to do that with scatter plots. So you see, every data type, they have their own corresponding visualization. And those are the basis, those are the foundations of higher and more complex visualizations. You can be fancy with visualization, that's fine, but make it to the point that you're not convoluting, okay? You're not providing so many unnecessary information in your visualization. Make it straight to the point. Because at the end of the day, the main point of visualization is to convey information, to convey insights effectively. Okay, that's why we create these visualizations from tables because as humans we evolved in a way that we can easily see patterns from visual representations, right? So we evolved that way, we developed that way. So if you would want to present something to a person, if you would present it in a tabular form such as this, even though you have the most accurate characterization through different measures of the things that you want to highlight, it would still be ineffective relative to a chart. So charts are always more efficient in conveying patterns and insights as compared to tables. Okay, but there are instances in which it's better to use tables, especially if it's not containing so much information, and if the data set cannot be presented in a chart because you have there some combinations of stuffs together. Okay, so in Power BI you can develop a matrix, a sort of table that would allow you to incorporate in your dashboard. Okay, so in this lecture we will start with iris dataset. So let's see this iris dataset uh, let me see, maybe through Excel first, just to have a bird's eye view of this data set, and then we will proceed with analyzing it, navigating through it using Python. So iris is a flower. Okay, I'm not sure if it exists in the US. Can you verify if it's in the US? If it exists in the US? Okay. Yeah, so this data set is one of the most famous data sets in learning data science. So we have the following. Oh, okay. Hasiba says it's my daughter's name. Nice, nice. Uh, my previous professor in graduate school, she's a she has a doctorate in statistics, and her daughter is also named Iris. It is because of the fact that it appeared since undergraduate until her doctorate. So it was kind of embedded in her subconscious that the Iris, that word would be a good name. So anyway, going back here, so the Iris dataset contains this following characteristics. So we have the sepal length, the sepal width, petal length, petal width in terms of centimeters, all of the measures of all the units of measurement here are on centimeter. Then we have the species. So we have Iris setosa, Iris versicolor, and Iris virginica. So those are the different um, species of this flower. So as you can see, there's a natural grouping, right? Same flower, but three different groupings. And we want to see the individual characteristics of each of the species. So is it that the Setosa species has maybe longer sepal length? And it could be that the versicolor has a wider sepal width. Okay, so we'll be analyzing that and comparing this different varieties or species of the same flower, right? So all of these are iris flowers, but they have this different types of species, and we will be doing that in this lecture through visualization. Try to see if we can infer, if we can arrive in a conclusion without going through um, inferential statistics, just by looking at the distribution in the chart. Can we say that one has a distinctive characteristic as compared to the other? You can do that, at least in the level of the samples. But if you want to say that in general, right? In general, if you take into consideration all of the population of, say, Setosa, would you conclude that they have longer sepal length as compared to the other species? If that's the question, uh, it will involve the use of an inferential method. Now, the question is, can you use t-test with this? Because I know by now you're familiar with t-test. And t-test, we said that you can compare two groups, but now we have three groups. Can you just do pairwise comparison? And for example, it would be Setosa and versicolor first, then Setosa versus uh what's the other one? Virginica, and then so there will be a pairwise comparison to see that there is at least one distinctive characteristic in one species as compared to the other. So we will be discussing those details, right? And we will see that if you do that, if you decide to apply t-test in more than two groups, then your probability of committing a false positive for the type 1 error would be increased, right? Mechanically, you can do that. Your software would allow you to run that, right? But by theory, your probability of committing an error, particularly saying that there exists an effect, even if it's not, is multiplied by the number of groups. So instead of 5%, it would now be 15%. And we don't want that. That's a uh, very high risk, at least statistically speaking. And this this very smart people from the past have found a solution for that, and they call it analysis of variance. So they argue that, okay, if you cannot do t-test for just for more than two groups, then we have another extended version of it called the analysis of variance. Okay, so as a preparatory for that, before you conduct any type of high level analysis, it's better to have a visual first, okay, of these things. Now let's move to Colab. So I'll be closing this data set. So let's first import this. Best, I think, if I would be sharing this to you so that you don't have. Again, I will not be focusing on the mechanical aspect, guys. I don't want you to be fixated into memorizing things. We're focusing more on understanding things and more about the principles. So this mechanical stuff, you can easily forget them in just a day or a week. You can easily search for them, but the principle behind, okay, is what I want to instill with you. So I shared in the chat box the link to my collab notebook so that you don't have to type everything from scratch. Okay, you can just um, move forward together with me. So let's first import the data sets that we want. So I will be importing everything now. So for me, it's okay. It's on this folder. I'll have it in here so that I can easily um, access them. So after successful uploading, I can just run this. So basically, um, I don't need this part. Don't need that. I'll be using two libraries in this lecture. So pandas, of course, this is indispensable because most of the time in data analytics and data science, you would be presenting and navigating through them in the form of pandas data frame. And why is that? Because in pandas data frame, you have all the tools that you need to manipulate your data set. Okay. And most of the libraries in analytics in Python are built on top of pandas. That's why it is indispensable. Now, for the second line, this matplotlib pyplot, okay, is a library for visualization. So let me send you um, the documentation for this one. Again, this contains tons of tons of attributes and um, tons of functions that you don't necessarily need to memorize. Okay, it's futile if you try to memorize them because there are just too many. So this is the most used library in Python for data visualization, primarily because it's very convenient to use. Okay, so we will be doing, I think, 5 or 6 different visualizations that would go all over the 4 levels of measurements that we talked about. Okay, so if you want to do more advanced visualizations like 3D and volumetric data, you can just refer to this website. This is the official website of Matplotlib. Okay, so going back in our Colab, so that's this library, and the typical naming convention. Okay, the alias for Matplotlib pyplot is PLT. This is how you would see it in books, in online resources. Okay, so once we run this, we would be able to see this first 5 lines, and we can do a further investigation by again doing um, basic statistics, looking into the summaries of it. So there are 150 observations in total. These are the averages for the different characteristics, and it seems that in terms of sepal length, right, it's around 5.8 in average. If we compare it with the median, it's almost the same, right? So we can say that there's no presence of outliers here, because if there's an outlier, then this would be very high as compared to your average, or rather as compared to your median. So the maximum, the one with the highest is 7.9, which is not outrageously high. Standard deviation is high for petal length. It seems that there are more variation around the mean with regards to this characteristic relative to the other, right? Because all of this are of the same unit of measurement, so you can compare um, this characteristics using the standard deviation. So the minimum for the sepal length is 4.3, 7.9. The range is not outrageously large. So we don't see any issues, right? We don't see any issues if we look at the summary statistics, because this is the first step. in detecting any problems with your data set. If you see any unnecessarily high or low values or even negative values and it's supposedly all positive, then you have to go back and look into your data as a whole. So the next step that we will be doing is to create a scatter plot. So the scatter plot is um, typically done in order to see the distribution of your values. Okay, so let's look at this blog. So I've included there a link so that you can have more information about scatter plots. So as you can see in here, we're looking at an example for price in thousands and price for homes. So of course, the prices of homes are tied directly with um, with the size, right? The size of the lot, or rather, not the size of the lot, but the um, how do you call that? The size of not only the lot, but the actual size of the house plus the lot. So we see a positive relationship, not perfect, because this is a statistical relationship, not a functional one, or rather, not a how do you call that? I'm always forgetting the term. Deterministic one. Okay, of course it's a functional one, but it's not deterministic. It's not just a conversion of one form to the other. So we're seeing right here for uh, much smaller houses, they're more cheaper, right? But as you can see, there's a quick jump. Notice the quick jump. So this is where we are particularly interested with. Notice the quick jump, although this is just a, oh, what happened? Okay. So we are particularly interested at a point where we could see a significant increase in the price. So if you will draw a box here, you would see that this is a homogeneous one, right? It seems that if you go from 2,000 square feet until below 4,000 square feet, the prices are comparable, right? But if you go over 4,000 square feet, there's a sudden jump to the price. Although at this point it's not yet conclusive because we're only looking at only two observations. It could be only a fluke, right? It could just this two things could just be an outlier for some reason. But if we increase our observations, right? If we increase our sample size, and still we observe the same pattern that after, while it's not perfect, but after 4,000 square feet, there's a clear indication that the price, right, suddenly jumps. Then, as an investor, what would you do? How would you turn this insight into a profit? If you're a home buyer and you're comparing two houses, one with 4 grand or 4,000 square feet, maybe a little over 4,000 square feet, and one with say 3,800 square feet, and the price difference is say 2,000, right, or say $200,000. Which would you buy? So you can create a cutoff, right? That you will only invest on this range in terms of size because the prices of the houses would be relatively lower as compared to when you go over a little over than that, say for 4,100 square feet. That's where the prices gets the prices get crazier. So knowing these things, you cannot easily visualize that if you just put the information in a table. You won't see that pattern, right? You would see the figures. Okay, here are the corresponding prices for the given size, but you cannot see this. So that's the beauty of visualization, and this is where you apply this particular chart called scatter plot. Okay, it allows you to see groupings, okay, and patterns from your uh, x and y variables. You can make it as a basis for a much higher analysis. Like seeing this, of course, it would not tell you how strong the relationship between square feet and price in thousands of homes, but it would give you a support to do further investigation, right? To do further investigation to quantify how strong that relation is. It's giving you a hint. It's giving you more reasons to invest more time and do your analysis further. So let's go back to our collab and let's see how we can implement that same visualization in our chart. So we have here a question. Is sepal length related to sepal width? Is there another way aside from going first to the visualization to answer this? Is it possible to answer that using summary statistics? So let's see sepal length and sepal width. So if you're just looking into the summaries, it's quite difficult to answer that question, right? Those are already summarized values. It's quite difficult to even get a hint if these two variables are indeed related with each other. If we go back to our records, right, it's even more difficult to get to derive information that would allow you to answer the same question. Because this is unstructured in a way that, especially if your data set is much larger, then it would be a pain to look piece by piece, pair by pair, and try to see if higher values are associated with higher values of the other, right? So the easiest way to have an idea if two variables are related with each other is to create a scatter plot, right? So here, I don't need to import this again. Apologies for that. I keep on doing that. So here we are invoking the plot function inside the PLT or pyplot attribute in matplotlib library. Okay, so PLT is matplotlib or particularly pyplot in matplotlib, the one that we imported earlier, this one. And for the first line, what we're doing here is, okay, we are plotting this columns, sepal length CM. These are just, you're familiar with this, column accessing, right? The square bracket. So this is our first column. This is our second column. And we have our marker here. You can change that marker to whatever you want. You can change it to a caret. You can even change it to a dot. And for the parameters of this, you can just refer to the document, okay, so that you can see all of the things that you can choose for the parameters, or in this case, the arguments. So it depends on your preference. I would leave that to you, okay? And we are not including any lines here, so we have none in the line style, but you can pass a regression line here. Okay, you can pass a regression line. I'll be showing it to you later to see if there's an evidence for a direct or indirect relationship. And we will be plotting in the x-axis. So this dot x label identifies your x-axis. So our length goes in there. See right here, we have the sepal length. And similarly for our y variable, we have the width. So you might be thinking, Jeff, can we interchange the position of these two? Yes. There's no the position of x and the y doesn't really affect how you could like your ability to visualize the relationship. You can switch to them and you're still good. And then this is an option to of course add the title on your chart. But if you're just validating, if there's a there's an evidence to proceed forward, then oftentimes you can omit that. Okay, but for completeness, I just added it here, so we have this title at the top of our visualization. And then this PLT show would actually generate the plot. Okay, it would generate and show you the plot. So let's try running this. So as you can see, it changed the marker because I changed it to dot. Okay, and we can change the color here. Say instead of blue, you want it red. There are these varieties that goes with the color parameter. So for the list of arguments that you can put in here, you can refer to the document. Okay, but yeah, I think the default one is black. If you remove this, it would apply the yeah, it's something like sky blue is the default one. Marker. So, any questions, guys, for this? So, what can we infer from this? So, in terms of the sepal width and sepal length, you see that there's a somehow direction going from lower values of both to higher values of both. It's not perfect, right? This is literally what you would observe from an actual data set. The ones that we saw earlier, those are the typical toy data sets, right? That would convey like a very evident linear or whether indirect or direct relationship. It's a typical toy data set. But here, we're actually considering an actual data set. These are actual records. So you would not see a nearly perfect, a nearly um, a set of dots that would follow a nearly straight line. That will not be the case. So you should have a trained eye in seeing, hey, while if you look at it quickly, it's like scattered all around. But again, look at from the origin, right? From the 0, 0, seems that this one is one. Sorry, this one is one group. This one is another group, right? Do you see that? There are two groups here. So this is group one and group two. In machine learning, there's a there's an algorithm that you can run even without taggings, like which one are versicolor, which one are setosa and virginica. The algorithm would be able to group them based on certain characteristics. You can look into k-means clustering algorithm, and you would see that idea that I'm talking about. Your algorithm would be able to pick up those natural tendencies and identify groupings. Okay, but you don't need the algorithm as for now, because what we're after with is to answer the question: are they related? The sepal width and the sepal length. So my answer here is yes. There's an evidence for me to proceed to much deeper investigation to quantify and see if that relationship is significant on the perspective of the population distribution, not only in the sample that I have. So you can easily answer that once you have this information, right? So I'm guessing that there's a positive correlation between sepal length and sepal width. Do you agree with me that there's a hint of a positive relationship? Do you agree, Grace and Hasiba? Or is it like looking into, maybe you should look at it this way. Maybe during the early 1900s, maybe around 1930s, when Picasso first introduced uh, his arts in Cubism, people were puzzled. Are you familiar with Picasso? I love Picasso paintings and Van Gogh, uh, particularly the Starry Night. So if you, maybe during that time when people saw this, they were thinking, "What the hell is that?" Right? Because during that time, at least starting from the Renaissance, 16th century up until around 17th, 18th century, people were into realism, right? And they're not used to seeing this kind of arts. But in the 20th century, early 20th century, these are prized artworks. There are hidden meanings, and it's different, right? So what I'm saying here is, maybe currently your eyes are not able to pick up the patterns, but as you gain more experience, you would see the value. You would immediately, right off the bat, see, okay, I see some patterns right here. Right? I see a pattern of positive relationship and negative relationship. I see a pattern of groupings that we can further investigate. Okay, so this is not just a random distribution of dots. It's more than that. Okay, so let's see. Let's further investigate. Right, but before that, these are just explanations from the codes that you have at the top, so you can just go over them. These are the some of the parameters for the marker. I don't usually mess up with these things. Again, you might hate me for this, but I'm not so much fan of um, making my graphs fancy. I make it straight to the point. Oh, here are the things that are important. But in terms of the say artistic side, I'm not so good at. Well, I don't invest so much time with it. Okay, I'm more into like the deeper aspect of the visualization. Now, um, we will be grouping because there's an evidence here, right? There's an evidence of a grouping, just like what I told you. Seems like this is one group. It also has a sort of positive relationship. But this is also another group that also exhibits positive relationship, right? The relationship of sepal width, and sepal length on this group is much stronger. If you look at the slope in this group, it's much steeper as compared to the group which has like a flatter um slope. Do you agree with me? Do you agree with me with that? Are you seeing it also? That it seems that this has a higher or steeper slope as compared to the group, to the hypothesized group at the bottom. This now looks like an amoeba under a microscope because of my drawing. Apologies for that. But are you still following, guys? Are you still there? Okay. Yeah. Thank you very much, guys. How about Hasiba? Okay. So moving forward, we have hypothesized that there are groupings in here. Okay, and with the knowledge that even though this is of the same flower, we know of the existence of the different species of the same flower, right? The Virginica setosa and what's the other one? Virginica setosa and versicolor. So we will be grouping now our data set. Okay, from one big data frame, we will be creating um, this setosa data frame. So this is for filtering. We did this during the Python session, if you can remember this. So this is for now Iris setosa. We'll just filtering it from the species group. So let me show you here. If we do a dot head again here, there's a column species, right? That we can use as a filter. So that's what we did here. We created a Setosa data frame, a versicolor, and Virginica because we want to separate them and compare the plots for each to see hmm, where are the overlaps because we only identified two groupings. So it must be that there are two groups that are comparable in terms of their sepal length and width. And there's this other one that is significantly larger, right, in terms of its sepal width, but has shorter sepal length. Notice the sepal length of this group is much shorter, right? Only stopped at around less than 6 centimeters. But their width, notice that it reached 4.5. And this group only has like the maximum under 4.0. So that's an insight. That's a very good insight. Oh, okay, it's freezing again. Give me a minute. I'm thinking of replacing this AC. Already 4 years old, and it seems that Uh, it already has a leak. So anyway, um, yeah, those are some things that you can see from this. Okay. At this point, those are just hypotheses, guys. Just a hypothesis, and we can verify it for further analysis. Now, moving on. So this is the point in which we filter our data set, right? So we can print that Setosa just to visualize it. So all of this are Setosa, right? All of this are Setosa, and we can compare the individual summary statistics for each of these different species. There are benefits in doing that, because it will give you a hint in which species are comparable. But if you would communicate that to other people, it will be quite difficult, right? So it's easier if you would just show it in graphs. And later on, if we have time, I'll be running an analysis of variance here to show you if there's an evidence looking at the population level, if there's enough evidence to conclude that at least two of the um, two of the species are different from each other, right? So yeah, let me just fold this one. Okay, now we will be plotting them against each other. So basically here, this is just similar in terms of how we did this earlier. So we are plotting first the sepal length. Okay, so first would be the Setosa. So this is for the Setosa species, and the other one is for versicolor. So um, you can change the markers for each. There's no problem with that. But here I just changed the color to highlight even more the different groups. So you do the same for versicolor and for virginica. There's nothing new here. It might look complex, but it's not actually. But it's actually simple. Okay, it's actually simple. These are just plots for different species, and we're just adding X labels here, centimeters in terms of length, and then the other one is for width. Okay, and then we just added a title here, and then we have a new attribute here, which is a legend. Is it needed? Um, yes, because your audience would easily see what the colors are referring to. Okay, so I have here location best. You can put it anywhere you want here. But I always use this best because, uh, for example, you have a data point right here. Oftentimes, if you just assign it to be on the upper right or on the lower left, it would overlap with those data points, or it might shrink it. Okay, so with that legend, if you go back to here and look into the documentation of that, um you would actually see all the legend. I need the PDF one. The PDF one is better. Um, legend you. There we go. Legends. X.legend. Mm, yeah, there we go. This one. This one. It could be it could be outside, although I don't. Um, Let me think. I've done this before. This one right here. It's effective if you have like multiple pairs, and if this would be relatively smaller, you want the legend to be outside so that it won't shrink further the size of your plots. But yeah, it's not always that you only have the best option in there. You can specify it upper left, lower left. It could also be with the first one. Um, it's outside. It's outside. I haven't done this before. Uh, like outside but on the top. Most of the time I've done similar to this, to the one at the bottom. But again, it's about your preference. I'm not that artistic, so I don't trust my skills um with this how do you call this? Uh, Adjustments in general. So it's on you. Whatever works. But the one that I want to highlight here is you can find all of the things related to the attribute in this Matplotlib um, documentation. So keep it handy. Again, it's futile to try to look at this. Look how complex this is. If you try to remember that, then you're wasting your brain's memory, right? So might as well just just um understand the principles, right? At least that's what I do. So here is the final result of that. So it seems that our intuition was correct. There are two groupings for the three species. So for the Iris setosa, the relationship between sepal width and sepal length is much stronger, right? Notice it's wider but shorter. However, it seems that versicolor and virginica have things in common in terms of their sepal width and sepal length. Notice this part right here. That part is an overlap. So they have overlapping characteristics. So if you do hypothesize, okay, that there exists significant difference first for virginica and versicolor, your resulting p-value could be large. And it would tell you that there's no sufficient evidence because they are overlapping. But if you do it either iris to setosa or versicolor to setosa or virginica to setosa, you're expecting to see a very low p-value because as you can see, even with only looking at the charts, it's already distinct, at least in terms of sepal length and sepal length, right? So that's what we're expecting if we do a statistical modeling. And that's the beauty of it. Even though at this point we don't know exactly the quantity, the measure of the correlation, but we're already expecting it to be positive. So it's a guide for you. If you run an analysis knowing this and you got a negative value, then there's something wrong with what you did, right? Because the summaries, the visualization doesn't relate with your result. So there's something wrong that you've done during your following analysis. You have to go back to your implementation, to your execution, and see what went wrong. So this kind of processes plus the summary statistics actually give you hints of what would you expect, what results would you expect from the succeeding analysis. So, yep, let's proceed. This is just an extension, the one at the bottom. This is just an extension of like what happens if say okay, before that maybe what if we run a complex analysis here? So what if we test on what if we test a hypothesis that at least of these two groups differ from each other. How can we do that? We can run an extension of the t-test called analysis of variance. Analysis of variance or ANOVA. Have you run this before, or have you encountered this test before, guys? Maybe you read it somewhere or in one of your tasks in the past. No, this is your first time seeing this one. Okay, so this is an inferential statistics. And what library are we using for statistical hypothesis? Stats models, right? So what I'll do is I'll go to the documentation of that stats models and see, hmm, how can I do, or what attribute in this library can I use to go and do ANOVA? That's how you do it. Go, go back to the implementation. So we have here an OLS, okay, an OLS um, function that would allow us to run analysis of variance. So let's try doing that. So let's import the function, rather the library import stats models.api as sm. And see, I feel like this Gemini is spying on me, even my voice, because as you can see, I don't know. Uh, I have a comment here, so it probably inferred from that. So um, yeah, this is what I need. Okay, so from this package, look at that, John and the group. This AI gives so much power to us. If you would be doing this from scratch, it would take you maybe 5 to 10 minutes to figure out the structure. But AI just gave it to you. But now we have to understand line by line if this is correct and what is it? What are the codes are pertaining to? So we are creating here a model. This is just a variable, and we're applying an OLS function from this library. So this OLS function refers to ordinary least square. So at the core, okay, at the core, linear regression and analysis of variance are the same for linear case. Okay, remember that. If you identify significance in your analysis of variance test, you would likely observe that if you run a regression analysis. It might blow your mind, but both of this came from just the same idea. The main advantage of using linear regression is for the purpose of prediction. But if you want to identify significant differences, you can also use the idea, okay, if that particular X variable in your regression model is significant, if you run an analysis of variance, that would also give you an idea that there exists significant difference. Okay, remember that. So, why are we doing this? Because we are hypothesizing that this group, this Aricetosa group, is statistically significant in terms of its characteristic as compared to versicolor and virginica. We're looking for that support in the form of the p-value. Okay? This is a good indication, but you cannot prove that this is um, statistically true. You need to have a formal test. Okay? So that's why we're doing ANOVA. So here, um, we are modeling sepal length CM. So we're starting with this. This is your dependent variable. Okay? So here, we are testing whether length is different across species. Okay, so this is called one-way analysis of variance. And we are modeling one dependent variable over different groupings, categories. There is another form, higher form of ANOVA called MANOVA, which is a multivariate case in which you're not only comparing one, but multiple dependent variables across multiple groups. We will proceed to that, but for now, I want you to be familiar with the univariate case. That is the ANOVA. Okay, so this is the dependent variable, the characteristic that we want to model, and this part right here is the species. Why do we have a C in here? Because we want to tell the system that the species variable is a categorical variable. Do you follow? If you have a categorical variable in there in your model, you have to put a C, the C um, parameter, and enclose that variable name inside the parentheses. Okay. Now we are referring to the data set DF, okay, in which we will be pulling out this column sepal length CM and species, and we will be fitting it. Okay. This dot fit function would execute the fitting of the linear model. And then we have here an ANOVA table. Okay, so there are different types of ANOVA, particularly with the residuals. But for now, we will use type 2. We will differentiate the three, but I don't want to burn so much time today to go over them. But we will reserve a time. It's just um, there's just difference about how we get the residuals in the different types. Types 1, 2, and 3. Okay, but I will not go to that today. The typical type that's being used is type 2. Okay, so we are here generating the model summary from the model that we have on line 7. Okay, and we are printing it. Now let me show you the result. Hopefully we don't encounter any error here. There we go. So what are we seeing? This is sum of squared errors. This is degree of freedom. And this is F statistic. And this probability greater than F. So what are these things pertaining? This PR greater than F is the p-value. Note that. PR greater than F, that just refers to your p-value. The thing with this is, in different packages, different programming languages, they refer to p-value in different ways. Um, SPSS is using SIG, right, John? Is it using SIG? SPSS? SIG dot? Do you still remember SPSS with p-value? Or are they
Yes,
using p-value? Yeah.
that's it.
SIG. Yeah. So SIG, this PR greater than F, prob. I think SAS use prob. So all of those different names, they're just pertaining to the p-value. Okay, don't be confused. And where does that p-value come from? From this F statistic. That F statistic is a non-negative, okay, statistic. And again, from statistic, we derive probabilities. Now, what we're seeing right now is a very low p-value, which gives us an evidence that the at least one pair of the species differ in terms of sepal weight. And we know already what it is, right? That group is Aricetosa. But look at ANOVA carefully. ANOVA doesn't tell you which groups are different. So remember that, okay? One weakness of ANOVA is it it is an omnibus test. It won't tell you which groups are indeed significant because it's null and the alternative hypothesis are set up like this. Its null is U1 equal to U2 equal to U3. And its alternative is at least one or at least one pair are different or yeah, is different. So basically here, our null hypothesis tells us that the means of whatever characteristic, in this case the sepal length, of group 1, group 2, and group 3 are the same. Okay? The converse of that is at least one pair, whether U1 to U2, U1 to U3, U2 to U3, is different. Okay? So once it sees an evidence that one pair, at least one pair, is different, it would give you a low probability. But it won't tell you, is it U1, U2, U3, U1, or so on. You can have a glimpse of that in your visualization, whether a box plot or this kind of scatter plot. Now, is there a way that we can see it using another method aside from visualization? Something like an after method, after ANOVA? Yes, that's called post-hoc ANOVA analysis. Post-hoc ANOVA analysis would give you an idea, okay, since the ANOVA test is significant, let's see which are indeed significant, okay? Now, let's look at the documentation of sets models in how to do that. Mm, Tukey. There's so many different um, post-hoc analysis, but the one that is famous is Tukey HSD. Uh, yeah, let me see. I haven't used this one. Um, it did not spark any anything. I don't remember anything I like. I I used something like multi comp before. Um, let's go back to OLS. There must be something in there that we can use. Mm. I would be surprised if there's no wrapped in method in OLS for it. Let's try Gemini if Gemini would give us an idea. So what I'll do with that, okay? Um, do the post token over here. Oh, no. Do the post token over. I don't want to copy that again. There we go. Let's see how. Oh, pairwise 2K HSD. Let's see that. Let's go back into the to the documentation 2K HSD. You see pairwise 2K HSD. Pairwise 2K HSD. Oh, there's no documentation about it. I wonder if this would work. Let's see. So we know the principle now, and we're just looking for the mechanical implementation of it. We know what to do. We're just looking for the functions to help us execute that. Okay. And in different programming languages, like if you do this in R, if you do this in SAS, there are different implementations for the same thing. So let's see what's happening here. So this is just a function, and yeah, so this would give us pairwise comparison, but I wonder why it's not showing in the documentation for some reason. Ah, there we go. Is it the same one earlier? Ah, no, this is a different one. Yeah. Let's try running this. There we go. And let's see. So we are looking at now are the pairs. So we have group one, Irisitosa and Irisiversicolor. And are we okay? This is surprising. Why? Let's go back here. From our visualization, what's only evident is this that the sepal length, okay, the sepal length must be different between iris and either versicolor or virginica, right? So we're expecting that that pair will be the only one to appear significant. We're not expecting that iris virginica, this green triangles, would be significantly different from that of the versicolor. It's surprising to see that the test is actually telling us that there's an evidence for it. There's sufficient proof that it's also the case that virginica and versicolor are also different in terms of sepal length. Do you see it? Virginica and versicolor. The test is telling that to us. Okay, we did not see that in our visualization. We thought that these are comparable, these two, because they are overlapping, right? Let's see if that would be the case for the width also. But do you have any questions before I proceed with the width? No questions, guys? Are you still following? Are you still with me?
Jeff, Jeff, can you hear me?
Yep, Grace.
Um, just because I'm still driving, is the sepal length on the visual X or Y axis?
It's the x-axis. Yes,
And
it's the
okay,
x-axis.
so it's finding. Yes, that's what I could maybe guess. Okay, thank you.
So basically here, oh, the data is speaking for itself. We have our own like intuition, right? Earlier, we have applied our own analysis to it through only its distribution, through this visualization that we're looking at. And what we concluded just by looking at the visualizations that the iris is the one that is significantly different from versicolor and virginica in terms of both the sepal length and the sepal width. But the data tells us a different story. It's not only setosa that has different lengths, but also versicolor and virginica, while there are overlaps, they're also significantly different from each other in terms of sepal length. Okay, that's what the the test is telling us. Looking at the statistics here, the mean difference is the greatest when you consider Setosa, the blue one, versus the Virginica. Okay, Setosa and Virginica here. So this is Setosa, the blue, Virginica is the green. That pair has the highest difference. Iris Setosa and versicolor are also different. Setosa and versicolor, they are also different. It is also true, right? Because as you can see, it's still further. That's our insights. That's our hypothesis early on before we conducted the formal test. But here's the surprising thing: the test is telling us that versicolor and virginica, while it has the lowest significant or the lowest mean difference, there is still evidence to say that they are statistically different. It means that if you increase the sample size further, okay, you would observe that the difference between these two, the orange and green, would be more evident. So the overlaps that we are seeing could be attributed to sampling error. Do you follow? Is there a possibility that this is incorrect or false? Yes. And that is called again an alpha error. We have a 5% chance that the effect that we saw is not really existing. Okay, but it's only 5%. Okay, 5%. So how do we report this? Okay, how do we report such surprising result? It's not actually that surprising. Okay, it's not something that would raise the eyebrows of other people, because at its core, these are two different species, right? Two different species, versicolor and virginica. So there might be some difference, right? Differences. So, however, as compared to Setosa, the difference could be less. Okay, the difference could be, or yeah, the difference between versicolor and virginica could be less relative to setosa to versicolor or setosa to virginica. Okay, so that's the result of our post hoc analysis with the sepal length. Now, what I want to do is to hit it also um, with ANOVA, but this time I want the sepal. It's not showing me the width. I will be having issues with the spelling if I don't copy this. Or maybe so as to have for you to have your own copy, I'll just put it right here and put it back to length so that you can replicate it later during labs with John. So putting this back right here, and I'll just copy this part and do the same thing here. Boom, then we have test now for the width. Okay, and let's rename this thing so they won't overwrite the. Okay, there's also an evidence for significant difference when it comes to width, right? Although not as much as compared to the length. If you compare the mean differences, right, this column of the ANOVA result, you would see that these are relatively smaller as compared to the difference that we had earlier for the length. Now, does it support our? Is it supported by our visual? The width is this. So yeah, I think so. These are the points that are just different, right? But this below that, they are already comparable in terms of width. The widest here is over 4, right? 4.5 to 4.0. But on this group, the widest is under 4. So these are the like the only ones that are significantly farthest from the others. And we have an outlier here, an iris setosa that has a short sepal and a short or a narrow sepal. So this is an outlier, guys. Okay, an outlier. But there could be so many reasons for that. It could be nutrition of that plant, like sunlight exposure, so many things that we need to understand further. That's why I find it odd that when analysts see outliers, they immediately decide to drop them. If you do that, then you're losing so much information. Like for example, here you did further investigation and find out that um, sunlight exposure affects the growth of this flower by a certain amount, right? Those knowledge, those information would be lost if you just decide to drop them just because it doesn't follow the rest of the group. So always remember that our model should conform with the data and not the other way around. Most analysts, and this is a common mistake even with my university students, they try to they try to force the data to conform to the model. That's the other way around. We humans, we develop these mathematical models to explain nature, to explain phenomenon, So it's not valid to reverse the process that we force the data to fit our understanding of them through the models that we have generated. And those models just came from nature also. So it's like reshaping the data to fit the container when it's fact the container should adapt depending on what would be the content, right? So that's a common mistake. If you would look into publications, if you would look into data science blogs, you would see so many data manipulation techniques that are just being done haphazardly. They don't even um, they don't even state the caveat of it that uh, there are repercussions of doing that. Of course, it would appear good in your model fit because you already manipulated it to fit your model. So, but it's totally wrong. Okay, so yep, so that's how we use ANOVA in Python. There's another package, or actually tons of package for data analysis in Python, but yeah, this one works. I'm good with it. Now let's look at this in a different way. Why not we fit a box plot here, right? But I think box plot would be better so that we can like compare, like consider first the the width, right? So I will not. mm, Let me see here. What if we want to look look at it using box plot so that we can objectively compare the groups or the characteristics by groups. So how would I do that? There's actually the easiest way. Copy that, or you can go to the documentation of matplotlib, but for the interest of time, I would take advantage of the fire here. Do this in boxplot, but I want only to fit sepal width. And we can just use this. Okay, look at that. There's also reasoning. 2 years ago, this reasoning, you'll be the one to figure it out. Crazy. How technology, how this particular thing has evolved, and I love it. I love it. It boosts efficiency so much. Let me see. So we have box plot. Okay, this seems right. Um, so the sepal width of the setosa, the sepal width of versicolor. Okay, that's right. And labels iris. Okay, that's also right. And Y label with. Oh, okay, perfect. This would run. I'm very positive that this would run. And this would give me the thing that I want. There we go. There we go. Perfect. Perfect. So now here, guys, this is called box plot. So let me go into the parts of this. Okay. So the upper fence that you're seeing at the top, this is Q3, Q3 times zero point 0.5 times 1.5. That's the upper fence. The upper fence, if any data point goes over that, it's a candidate for an outlier. If it's go below that, like this one, the lower fence, it's also Q3. It's the um, Q3 minus QC 1.5. That's the formula for this one. So that's the lower fence. So this dots or circles that you're seeing, those are candidate outliers. And we have seen that this could be the one at the bottom, and this could be the one. But I doubt that this is. That's why I said candidate. I don't feel that this should be identified as an outlier, even though your box plot tells you that it could be. But looking at the scatter plot, I guarantee you that it is not an outlier. So that's why I added the adjective candidate. Okay, these are candidate outliers, but you need to verify further if there's a strong evidence. This has the lower one has. Okay, this is a positive outlier for me. Now, okay, so these are the fences that we can use in order to identify candidate outliers. This yellow, orange line at the middle, that is the 50th percentile or the second quartile, Q2. That's the median. Okay, this is the median. The yellow or orange horizontal line. This is Q3. The upper box is the third quartile. This is Q1, the first quartile, 25th percentile and 75th percentile. So those are the parts of box plot. In fact, if you go into just looking at it, parts of box plot, you can see those details. Yeah. So the use of that is to have a comparison of distribution, and at the same time, um, give you an idea of the existence of outliers or potential outliers, I should say. Now, why did I generate this? Okay, because it's easier to compare characteristics if it's on a box plot. Okay, if the box plots, okay, are significantly farther away from each other, then you have more indication of difference. Like if they're not overlapping, even the whiskers, these are called whiskers. If, for example, this thing is like right here, okay, if it's right here, the whiskers and the box are there's no overlap between this and this supposedly, then that's a very strong evidence of difference. Okay, now let's do the same thing with how do you call this, the sepal length. I think I just need to adjust the name here to length. That should work. Okay. I hope I got the correct name. Oh, it would tell me anyway. Ah, I got it. Okay. Now for the sepal length, you would see that in terms of rank, Virginica has the longest sepal, followed by versicolor, and then lastly setosa. So it seems like for both the, if you look at it this way, setosa seems like the widest in terms of sepal width, but it seems like it is the shortest, right, in terms of sepal length relative to the other species. So you can easily see that using box plot. It will not be too evident here, but we have seen that, we have hypothesized about that earlier. But with box plot, it is very evident, right? Well, box plot is one of my most favorite plots because it's very useful. So, yep. And again, now it was evident that this is really this lowest value of Virginica is actually an outlier, even for the case of sepal length, which is good. We've identified that earlier. Okay, so that's box plot. It's very useful. I always generate that, especially if um I'm comparing groups. Okay, so this is nice. This is a nice box plot. The the ranges are comparable, and you see this pattern of um, order in terms of the length of sepal for each of the groups. Okay, so yeah, I think that's where we stop for today. The other remaining parts are just extensions of this and other types of visualization that we can cover on Saturday. So I'll be leaving you with John. Are you good to go? Okay. Um, let's see. Let's see if we can finish the Saturday session. This would take me probably around mm, maybe an hour to finish this. I may want to add density plots here. This is a histogram, and oftentimes it's better to see the density plots because it's cleaner, it's smoother. And then the good old bar charts. Yeah, we will be talking about them. Multiple charts on the same window. So yeah, I think that's all that we have for today. And so for Saturday, we'll complete the coverage for the different charts. And then on Monday, let me see the curriculum for statistics. I think John posted it here. I want to stay structured. Um, Sometimes I get carried away easily with the topics. I told myself that I would be touching only the surface part, but yeah. So Monday would be probability theory. Okay, probability theory. I'm thinking of how
I think Sir Jeff accidentally closed the tab for the MS Teams.
Okay, apologies. I misclicked the leave button. So on Monday, we will be starting with probability theory. And here's the challenge for me. I would be needing to think of how can I discuss probability theory in a non, I should say, in a not so heavy mathematical way, because theory is the foundation of statistics, and it's a heavy math. Okay, even mathematicians find probability
Those
difficult.
those are the things that I'm telling them. Like yesterday on our session, like the reason why statistics is so heavy on our course is because we are trying to compress this so many subjects
Concepts.
into
Yeah,
to this couple of weeks only.
yeah. So that would be a challenge for me because, um, yeah, probability theory is very heavy on math. It's a combination of so many things. It's a combination of calculus, matrix algebra, all of those things. But of course, we will not be going through that because not be you'll not be proving stuffs when you apply for a job unless you would be teaching in the university. So in the industry level, I'll just give you the understanding, the inner workings of it without going over to the mathematics. Okay, like where are we using binomial distribution? What are the events that we can model with it? Like, is it always like tossing a coin, or where are we using Poisson distribution? Can we model it to predict how many people would be riding a bus at a given time, or be waiting in the bus station in a given time? We How about modeling, like, um yeah, basically I will not go over to the mathematics. Okay, it will be just be more on the applied part. But this is what I'll do. I will show to you how to generate those probabilities in Python, because there are interviews that are asking about that. Okay, particularly those top companies. They would be asking you to generate the probabilities from this given type of events. So, but again, it's just mechanical operation that eventually AI would be taking over. So if you focus on the mechanical aspect, you are in big trouble. Because as you can see, if AI can do it, then why focus so much on the mechanical side? You should focus more on the principles and understanding and inner workings of things, right? Understanding more, because with mechanical stuff, just have to have an AI assistant. Just tell it what to do. At least you know what you want to do, okay, and you know the details, um, the important stuffs, the nuances of those things. So that's what we'll do. So I'll be leaving you with John, Grace, and Siba. Um, yeah. See you on Saturday. Bye bye.
Alrighty, thank you. Okay.
Thank you, sir. Okay. Hello, Grace and Hasiba. So I think you still have a lot of heavy discussions today. So hello for that, Hasiba. So yesterday I already created the file for the wait. Let me transfer on the laptop so that I can share screen. Don't worry, this would be quick. We will not have any activities to perform today, so that you will take your time. Okay. So as I've said, we have exam on statistics. I think yes, the actual exam on statistics, but I'm not sure of its format. I will still talk to Sir Jeff what will be the format of our exam in statistics. If that will be conceptual or you will handle your own data. But I think if you will handle your own data, like you will perform statistics on your own data, it will be focusing only on the simple statistics, like the simple tests such as the dependent t-test and independent t-test that we have covered yesterday. So today, let me just show you the thing that I prepared on the canvas. So you can actually see it on their canvas. I already posted it. Wait, did Jeff attended the class today? I didn't see it.
Jeff
Wait.
stopped by, said he was somehow gonna have
Okay.
trouble joining, and then yeah, Sir Jeff mentioned him having the new job.
Mm,
So
so let's congratulate Jeff maybe when we have a full hands on. So just like what I've said yesterday, you will perform your own statistical tests. tomorrow. And you can start it by now. Like, I will not give you another activity for today. I will just show you this thing. So I posted 4 files all in all, and these files are by pair. You can already see it on the canvas. We have the dependent t-tests and also the independent t-tests. So let me show you the contents of this exam. So I think it's still on my desktop. So I will just show you that so that I don't need to download it again. So I I created this exam yesterday. So I hope every steps here will be very clear, because these steps you can apply this in any other steps while you are you are testing a hypothesis. Okay, you are conducting statistical testing. So for example, here in the independent t-test mock exam. So again, this is just a mock exam. um this is a preparation in case that your exam will be a statistical test. So here we have this problem: assessing the effects of a new supplement on athletic performance. So we have this background wherein a sports nutritionist, so we have a researcher, is interested in evaluating the effectiveness of a new dietary supplement designed to enhance athletic performance. So you have this new drug, somehow new um, supplement that is designed to enhance athletic performance. And the problem is you need to evaluate it. You need to determine whether its effect is positive or whether it is effective. Okay, to do this, they conducted an experiment with two groups. So here we are clear that we are dealing with two groups of athletes. The first group or one group will receive the new supplements, while the other group will receive the placebo or something like candy, but they don't know that it is just a candy. This is the neutral drug, that we can think of it that this is a type of drug that doesn't have any effects. Okay, after 4 weeks, the experimentation goes like this. After 4 weeks of supplementation, the performance of each athlete is assessed using standardized athletic performance tests. So here are the details. All in all, we have 80 athletes assigned randomly in two groups. So we have 40 athletes for each group. So group A will receive new supplement, group B will receive placebo, and the duration of our experiment is 4 weeks. And the outcome measures of this is the performance score based on the standardized athletic performance tests. We have somehow have this standardized athletic tests in which both of the groups will perform the same thing, and there is a corresponding scores for that. So let me open this file, independent t-test mock exam. So the file looks like this. So we have the athlete. This is just the athlete number, or the respondent number, the first column. So all in all, we have 80 participants in our experiment, and they are divided into two groups. Group A, so up until this line, and Group B, up until this line. So you don't need to count it manually. They are There are 40 participants for Group A and 40 participants for Group B. And these are their scores. So what you need to do is this following. So let me go back to the independent t-test. So the research question is there a significant difference in the performance scores of the athletes who received the supplements and those who received the placebo? So that is the thing that we want to determine if there are differences in their performance. And to solve this problem, I also included the step-by-step process in which you just need to fill in, like
what is the problem of the study? So it is already given on the background of the problem. What is the problem of the study? So you can tell that the problem of the study is about assessment of the supplement. And based on that problem, you should be able to construct your null and alternative hypothesis. So for the null, you will just say that regardless of the supplement or regardless of, of the thing they receive, it is either supplement or placebo, there's no difference in the performance, or the performance of those athletes who receive supplements has no difference on those athletes who just received the placebo. And then, of course, you need to state the alternative hypothesis, which is just the opposite of the null hypothesis. And then here I provided you all of the statistical tests of your choice. But you need to choose between independent t-test, wedge t-tests, and Mann-Whitney U-tests based on the characteristic of the data. And I also included here the character, like the checklist of the data. You should use independent t-tests if like group A and group B follows normal distribution. So I gave you a clue. You can use QQ plot, you can use histogram, and Shapiro-Wilk tests. Second checklist, the second on the checklist is they should have equal variances. And for this, you should use Levin's tests. So you will test whether the variance of group A is equal to the variance of group B. Okay. Okay. So that is the checklist for independent t-test. If these two is satisfied, you will use independent t-test. But what if one of these is not satisfied? So batch t-test will be used if this is a typo error. One group should be group A. Group use this t-test, batch t-test, when group A and group B follows normal distribution. However, they don't have equal variances. So they are they failed this tests, this second test. What if one of them is not normally distributed? So use Mann-Whitney, regardless of if they have equal variance or no or not. If one of them, group A and group B, has at least one that's not following normal distribution.
Which
Two,
test is for normal
this
distribution
one,
again?
the Shapiro-Wilk tests, you can also use the QQ plot and the histogram. For the histogram, it should be shaped like a bell. And for the QQ plot, it should follows the red line at the middle. All of this, you don't need to construct it from scratch. You can use the codes that we have yesterday. But of course, you need to change some of its components for it to be applied on this file. So you need to upload this file on the Colab and then take note of the name of the columns as well as the name of the components. And if you can successfully change the components that are on the things that we performed yesterday, then you can perform this statistical testing. So here you will choose statistical testing, but the appropriate testing will depend on the result of the normality test and the Levin's tests. Next, you will define level of confidence, but I gave you the level of confidence for this problem. Just use 95% level of confidence. We also have the rejection criteria since we are at the level of confidence with 95%. So reject null hypothesis if the p-value corresponding to the test statistic is less than 0.05. So Remember, all of this will give you p-value. Okay? But first, you need to determine who of these three should be the proper test to be used. So either of the three will give you a p-value. Based on that p-value, you can reject the null or do not reject the null. The next one is to perform the actual tests. So this includes the testing of the assumptions at number 3. So you have this test of normality for groups A and group B. Next is the test of homogeneity or for the equality of the variances of group A and group B. And of course, the last is the actual test for comparing the groups, because these two will decide who will be who will be the statistical test out of these three choices is the proper test to be applied in the data that we have. So that's why I just have here statistical test for comparing. So among those three, among the three tests. And then based on the p-value that you would get there, what's the decision? Do we reject the null hypothesis or not? And if, for example, we rejected the null hypothesis, what is its interpretation? What can we conclude? Is there a significant difference between group A and group B? Or there's no significant difference? And based on that answer, you can deduce or you can have this decision whether the supplement is effective or not. Let me give you a clue. If there is a significant difference, of course, if there is a significant difference between group A and group B, okay, there significant difference between those groups. Therefore, the supplement is effective. Somehow it has an effect. Okay, it has an effect. And if you will open the other test, so that's for the independent t-test. Let me go back here. The files that I showed you is this two files, independent t-test mock exam and the independent t-test CSV file, which contains the scores and the details that we need to perform the test. If you will open the other file, like the dependent t-test and then the dependent t-test CSV file, let me find it first. Dependent t-test CSV file, the structure is almost the same. You still have that step-by-step process, but the data set it is in the format of before and after. Okay, before and after format. That's why we are using dependent t-tests. Same set of employees, but we took information from them twice. It is before and after the treatment. So let me read the passage about the dependent t-test. What's the problem here? The problem here is the impact of training program on the employees' productivity. So the background goes like this. A company wants to determine the effectiveness of a new training program aimed at providing employee productivity. To do this, they measure the productivity of the employees before and after the completion of the training program. And the productivity is assessed using the number of tasks completed per week. So let us go back to the data sets. So these are the employees. So for example, employee 1. Before the training, each week, this particular employee completes 27 tasks. But after the training, this employee, the same employee, can complete 31 tasks per week. The same case for employee 2. Before the training, this employee can complete 28 tasks per week. But after the training, 30 tasks per week. So using that information, so you need to test whether um there is a significant increase in the number of tasks completed by the employees after completing the training. Like the same scenario a while ago, does the training has an impact on the productivity of the employee? And you can answer the problem by comparing the before and the after data. And I also provided here the step-by-step process to solve the problem. What is the problem of the study? So you need to specify it. You need to distinguish it before you proceed to the next parts. Now, what's the null and the alternative hypothesis? Even the simple way of writing it, like the before and the after is equal, or the before and after is not equal, something like that. Even that simple way of writing null and alternative hypothesis will do. But it would be helpful to you if you will also write the null and alternative hypothesis in detail, because you will use that information to write the conclusion and interpretation. So 3, what is the statistical tests? So we have, as of the moment, we have 2 choices. Dependent t-test, we will use that if the differences between the before and after scores is normally distributed. So for this, I gave you the clue on the other file. If you are testing for the normality, you will use QQ-plot, histogram, and the actual test, the Shapiro-Wilk test. Like the way you test the normality for this is the same test, in which those tests are the things that you have applied on the other tests. So everything, like every clue is provided on all of those files that I given. Okay, if the if the differences between before and after is not normal, then you will use the Wilcoxon test instead. By the way, you are free to use ChatGPT or online softwares, like you are free to use like when to use how to use Wilcoxon sign rank tests in testing this before and after groups, step by step, including the assumptions. And you would see that it will include the testing of the normality, and it's fine if you will use that. Define level of confidence. For this, I also just set it to be 95%. And because of that, we will reject the null hypothesis if the p-value is less than 0.05. And then 6 is the performing of the actual test. First is the test of normality for the differences. And now the statistical test for comparing the groups, either dependent t-test or the Wilcoxon sign rank tests. And then based on the p-value that you would get here, do we reject the null hypothesis? If we reject the null hypothesis, what can we conclude? Is there a significant difference between the scores before and after? Or let's say we did not reject the null hypothesis. What can we conclude here? And then somehow interpret what's its interpretation in the context of employee productivity. Like, for example, you rejected the null hypothesis. What does it mean to the training program? Is the training program effective or not? And what I can suggest is to have a detailed documentation of the processes that you are using. On the steps that I provided, you can stick into this and it will guide you to finish the activity. Together with this, you can wait. This is the dependency test, right? You can use the dependency tests IPYNB file that I shared with you on the Discord. The same case for the independent test. The structure is almost the same. The tests are there, but you need to replace the name of the columns, the name of the table, the name of the file in order for those codes to work. And that activity is the only activity that you will perform tomorrow. Like the entire hours tomorrow, 3 hours, will be spent for you to complete that exam. Like we are like somehow we are having an actual exam. But remember, this is just a practice. This is just a practice, and I I have a feeling that this might be the format of your tests on the exam for statistics, like the application. Any questions? Grace
Can
and
we
Hasiba.
still ask you, like, if maybe we're stuck or something, can we still ask you questions since it's a mock? Or what?
You can ask questions, but as how can I put it into words? As much as possible, try to figure it out first. Like use all the tools that you have for you to come up with a solution. Tomorrow we can still join the meeting. We can still join the meeting. However, if you will ask something, I can suggest that we can just utilize the chat box for that. We're still in the meeting, but I will answer you through the chat box. Or you can also send screenshots of your code on the Discord, or maybe on also on the Teams. Like, what's the problem here? And I will try to reply as much as possible. If I think that the reply will not somehow spoil you the the actual way to do it, I will answer it. But expect that I will just give you a clue. But maybe on Saturday, this is my thinking. On Saturday, we will look at your codes. Like, what are the things that we have a problem with? So, what I can suggest also is while you are doing this activity, list down the challenges that you have encountered so that um, we can try to create an activity wherein it will focus on the difficulties. Okay? Any other questions? Is everything clear? Is the Word file detailed enough?
Yeah, that looks.
Okay.
I like the guided
By the way,
process.
this file, again, this file, at any statistical test that you will perform, whether you are conducting chi-square, correlation analysis, linear regression analysis, multiple linear regression analysis, these 8 steps that I provided is like the blueprint of how can you conduct the testing. Like, first, you need to define what's the problem and then state what's the null and alternative hypothesis. And as of the moment, we only have one null and one alternative. But uh, I'm not sure if we will cover it because our statistics is too heavy for our class. What I'm saying is the statistics that we have is quite advanced for IDA. Some of these tests are covered in the ADA class, like the logistic regression analysis. So those stuffs. So but even if you perform those tests, these are the steps that you will follow. What is the problem of the study? What is the null and alternative? If you go higher level, the number of the null and the number of alternative hypothesis might increase, but still you need to specify it. And then again, going over the assumptions will tell you what the appropriate test to be used. That's always the case. Like statistical test is not one size fits all. You really need to dissect what's the property of our data. Is it normal or does it have equal variances? That's why you have many choices. The real challenge for me, I think, based on my experience, I'm not saying that my experience is so many, but maybe on my 2 to 3 years of experience of handling data, especially statistical tests, the most challenging part is to determine what's the appropriate tests. Really, that's the most challenging part. So I can understand if you choose the wrong tests. But I provided you the cheat sheet, somehow the cheat sheet that what are the basis when to choose the Welch T test? What's the basis when to use the Mann-Whitney U test? I also this one is important. Maybe you are thinking you are always using 95% level of confidence, so it is defined that the rejection criteria is 0.05. But um, just to that you remember, if you are on the medical field, I think Grace is on the medical field, and you are experimenting on new drugs, new formulation of, let's say, amoxicillin, paracetamol, so some of the common drugs that we are having in the market. If you are formulating a new drug that is more effective than those drugs, this level of confidence should be higher. The minimum is 99% because you will test that for people. People will use the product and it might severely affect their health if you have this little error. So as much as possible, we are minimizing the error. So here the error is 5%, 95% level of confidence. The error of committing wrong decision, like you will either reject or accept the null hypothesis, right? The error the error of committing wrong decision is just 5% here at 95% level of confidence. But if you are testing the products for people, as much as possible, we want to minimize the error. If a life is at stake, the higher the confidence level that you would see. But here we will just use 95%. And it is 0.05. Like if you saw a p-value that is less than this, then we reject the null hypothesis. It is easier to reject the null hypothesis if we are just testing the 95% level of confidence. But let's say this is 90%. We have a lot of space for error. So that is 0.1. So you will just reject the null hypothesis if you computed a p-value that is less than 0.01, 0.1 rather. And what I'm saying is this structure of 8 steps, you would see these steps at the books, statistical books, like 5 to 6 steps, but here I made it 8. Like my own way of doing the statistical test, I am sharing this to you. And I hope this helped you understand the process of statistical testing. In the Philippines, if you know how to handle data, if you know how to conduct statistical tests, students, what else? Students from bachelor's degree, senior high school, up until the master's degree, depending on your capabilities of handling data, they will search for your help. And each help corresponds to some big compensation, something like that. Like um, Sir Jeff is also doing that, especially when the season is at the universities thesis writing, and they are on the part that they will they need to pass a thesis, and they need statistical testing. That is the time that there are many students are trying to get help from statisticians and those people who are statistics practitioners. So it would be an advantage if you know how to conduct even those um, simple tests like dependency test and independency test, because the higher level of statistics, like the logistic regression, you would just see that on the master's level, on the PhD level, or let's say research by the government. But the most common tests, it includes the dependent t-test, independent t-test, ANOVA, the one that was covered by Sir Jeff earlier, as well as the chi-square test and correlation test. If you can master those statistical tests, it is easier to expand, because what's important is the foundation. Like when to use this test, when to use that test. It is founded above that test that we are discussing right now. So I guess what I can say is good luck on your mock exam, and do your best. Do your best. I don't be pressured. No need to pressure yourselves too much. If you can't get the right codes right away, don't don't panic. That's the thing that I can say. Don't panic. It's part of the process. In programming, 70% of the time you will get an error. 30% of the time that is the time that your codes will run. So expect that you would have a lot of errors. You would have a lot of mistakes in writing the codes, whether it is a typographical errors or technical errors. Your code is the big problem. Yes, I agree with that. But yep, it's part of the process. Even me, like the one who is teaching you statistics, even me, I don't I don't have this ability to write those codes from scratch. I need some guidance from the internet. So there's no there's nothing wrong if you will use AI tools. What's important is you understand, like you utilize it in the best way possible. You understand its output and you know how to take advantage of its output. You can search on the internet, and the good thing in statistics is the structure is always the same. The structure is always the same, just like what I showed you earlier. So if you are testing the normality, you will always use QQ-plot, histogram, and also the Shapiro work. Or if you have some other test that you want to try, such as Kolmogorov-Smirnov, the structure is the same. So don't pressure yourself too much that if you can't do this thing, then you can't learn statistics with Python. That's not true. It's part of the process. We're still on the part that we are learning I'm sure I'm not in the position to tell everyone that it is that life is a lifelong learning, but I guess in the field of statistics, that's the thing that I can say. Like, statistics is a heavy subject. So if you don't understand it the first time that you saw it, don't panic. We'll try to get solutions on those errors. It's part of the process that we get errors. Okay, so any questions? Any concerns? By the way, I set the deadline of this on Saturday or Sunday, I guess. July 14. It is available until July 14. I learned 40% from statistics. It's okay. 40% is a lot in statistics. 40% is a lot. So if you learn 40% from the statistics class, like everything that we have covered up to this point, it's a lot of progress. I can say that. You can't absorb 100% of the things that we will talk about right now. It's impossible to observe it in just a short period of time. Maybe it's possible if you will watch the video again and again, or you will watch other videos online on YouTube, or you will read documentations online, and you utilize the power of ChatGPT or any other AI tools. It will speed up the process, but like understanding whole statistics in just span of 2 to 3 weeks, it's okay if you just learn 40%, because I can see that it's impossible to learn 100% of it. Unlike the other tools that we have used, that somehow we have understanding of everything. Somehow we have the idea on what to do. But on statistics, there are a lot of times that we will be just stuck. To tell you honestly, previous months, I accepted some clients who are asking for statistical services, and there are tests that I think of for an entire 4 days. Like, this is a new test that I did not encountered previously, so I studied it in order for it to be applied. Like, I assessed the characteristic of the data, of the format of the data, and the data I handled it for 4 days. So it's a lot of mental work. So it's fine if you will have a hard time on statistics. But in this case, we'll try to lighten it up. Um, to be honest, we are trying our best in order for this big statistics to be uh, an edible pill, something like that. That's why Sir Jeff is also challenged on the way this is discussed. I am also chatting Sir Jeff all of the time. Like, I am requesting for a call outside of the office hours. Like, I want to have a discussion on how should we discuss statistics at your end based on your feedbacks. And the good thing is he is open for those suggestions. So if you have concerns, if you have suggestions, that just tell it, and we will try to create a solution for that. Okay. So that's pretty much it. We don't have left activities now. You can just focus on the files that I posted on the Canvas. Tomorrow, maximize your time on doing that activity. Okay? If you have a question, take a screenshot of the part of the code that you have a problem, send it to me through even the Discord, even in the Canvas. I think there is a messaging there. You can also contact me through email. You also have a choice to paste it in our chat box at our meeting, but it's better if you will personally message me so that the questions will be organized. Okay? And I will try to reply as soon as possible. Like the reply that will not spoil the answer, but will definitely help you on the problem. I will give you clues, something like that. Questions. So we don't have to join. Actually, yes. We don't have to join the class tomorrow.
Okay. Okay. I don't have any questions right now, but I probably most likely will. So thank you.
Okay. If you have a problem, Grace, contact me through the Discord. I will try to log in my Discord on the smartphone so that I can reply even if I'm outside the house.
Yeah, see the notifications. Okay.
Okay.
Thank you.
Okay, thank you,
Bye.
Grace. Thank you, Asiba, and good luck. Good luck on your mock exam. I hope this will help you. Thank you.